welcome you here at the technical forum of the group exhibit Hydrogen, Fuel Cells and Batteries. So come in, have a seat, have a drink on the house and enjoy with me our next presentation dealing with the topic My Home is My Power Station. Benefit of photovoltaics and battery storage to owner and grid. And welcome here with me the Head of Department Photovoltaics from Zentrum für Sonnenenergie und Wasserstoff-Forschung Baden-Württemberg, Dr. Jann Binder. Give him a big hand, please.
Okay, thank you. Good morning, if I may still say. It's 12 o'clock. Nice to see you here with your interest on battery storage systems. Basically, I'm talking to you about what can it get to you if you have a battery or a storage system, thermal storage system in your house, and what benefit can it also do to the network, because quite often PV system owners are being criticized for abusing the grid, feeding too much power in. Okay, so I'm coming actually just as a background from ZSW. This is Center for Solar Energy and Hydrogen Research. An old name, 25 years ago already there was a big hype about hydrogen, how to store energy if it's produced maybe in the desert. So that's where the name is coming from. And we are still working in these areas of photovoltaics. So we do actually have some development, thin film technology development. We have a plant, a little research plant to produce these cells. We have fuel cell activities, are in hydrogen technologies, in electrochemical storage, which means power to gas, basically with electricity generate hydrogen and then methane. We do also lithium batteries and system analysis and consulting. So, and I'm coming from this department of photovoltaics modules and systems, where we actually do tests on PV systems, and this is the topic of today, the grid integration of PV plants. So I'll be looking a little bit at the network and local perspective, balancing generation and load, PV generation, wind generation, and then what is your local opportunity to help in this balancing of energies with your local installation, and what can you do for the grid with it. So this is the picture of our energy system. Of course, the old one, fossils, they were just producing and you were using it, and now you get these fluctuating sources, and therefore you need the storage, you need a battery. Of course, you have pumped hydros, but you really need long-term storage with power to gas, for instance. You feed in with the natural gas. So this is what you do on the top, but what can you do here at the home? You see already that if you talk about natural gas, it comes to mind already, well, let's just match the heating also in the production, because then you get more opportunities to actually deal with the changing generations. So if you look at your house now, and what is your consumption in the house? All right, you need heat, a certain amount. If you do that heat generation with a heat pump, because you have this coefficients of performance over the year of maybe 3, then you might need 10,000 kilowatt hours thermal, then you end up at 3.3 kilowatts electrical. For the heating, then you have some appliances which add some other electrical demand. And you might have a PV system on the roof. And it's not too difficult if you have a well-insulated house to make this sum of PV generated over the year bigger than what you're actually using over the year. 10,000 kilowatt hours from the roof works. Now the problem is it's not in time. No, already you have this offset, and I think that's basically what we're talking about. How can we deal with this offset? Obviously, I want to get this energy which I have during the noon hours back to the evening hours or in the mornings. What do? I basically have electrical storage, and I'm using thermal storage then. With the heat pump, I always have a bit of thermal storage. Even in summer, I want to have a shower. So even in summer, I do have some use. And the question is, how much of it? So what we're dealing with is now controlling the storages, trying to see what are the potentials, and trying to be helping to get sustainable and stable cost of energy by basically knowing what my invest was and using this electricity myself. Okay, so what we're talking about is how much consumption can I do myself of the PV generated energy, and in a way, how autark or autonomous am I? Do I get autonomous? Obviously not quite, so it's a level of autarky or autonomy that I get. And the end, the grid load reduction. So let's do the balance. Input, solar radiation and heat. The rest of it I get from the grid. What's my consumption? It's the household appliances. It's whatever leaks out of the house. It's hot water and spatial heating. And I'm dealing with storage to do the buffering. Okay, that's the example. You don't have to remember. The slides are on the web. But I'm just using a small house, 140 square meter, 4 inhabitants, just as an example. You can do any other one. I'm just saying that my tanks are set at 35 degree for the aerial heating and at 50 degree for the hot water. And I'm giving PV a little bit of an advantage. Like if there's PV, it's allowed to heat up the tank a bit more. That's a simple way of giving it a bit of a priority. And now it depends what you use as heat on the building. You have different building standards. If you take a house in Germany, 2009 standard, then at minus 12 degrees outside it, you have to pump 5 kilowatts in it. Otherwise it gets cooler. Yeah, so this is your heat load of the house. If you do that and you just simulate it over a whole year, what you arrive at that at the end you needed 10,500 kilowatt hours per year to keep it warm. Just simulating with the temperatures that you had for 1 year, 2011. And if you do that with a heat pump, in every time slot, every hour, we basically calculate what was the outside temperature, what was the heat needed, and so you get every time you get sort of a efficiency of the heat pump. And if you add that all up, then you get to this yearly coefficient of performance, and you also can see what kind of electrical energy did you use. So this is really not just taking straight that number of 3.3, but it's an hourly calculation of every event. What is my thermal level and the storage and so on. Okay, if you compare that now, this was for the heat. What do these people use for appliances? Just to get a feeling, it's quite interesting to see that for your appliances you use about as much as for the heating. So, just to get a feeling, if you have, now this is that house from before, if you have a zero energy house, you can see that with a zero energy house, you only need a third of it, so your thermal demand becomes actually very low compared to the appliances. So if you want to deal with thermal storage as an advantage to actually shift your load, it works only in houses which are not so well insulated, because here all you need is the hot water. But if you have bad houses here, old houses, and the standard in Germany is still somewhere here, you need quite a lot for heat. So there's a lot of potential to put PV into the heat. All right, so what is the result at the end? If you just take it, the dashed curve on the bottom, this is basically just without heat to start with. Then the overlap that we have seen from use of electricity and your generation, like this yellow bit which overlaps, it's about 30% over the year. So only 30% of the energy can be used without doing any storage. Now here's the heat load of the houses, and if I start now to take just a heat pump, well, if you have a very good house here, obviously you can't do much increase of self-consumption, like how much of the energy that you harvest from the sun can you use. If you start to do storing, you can get up to quite high levels of using your own electricity for heating if you apply large storage. Well, large. You need 1,000 liters, 1,500 liters of thermal storage. For the small house, for the well-insulated house is about 1,000 liters, which is not really too big. You can get this into your basement. So let's look at it this way. The left charge is here just without heating. That is with heating. This is now to do it slow. This would be the point where you have a PV system which delivers you as much electricity over the year as you use for appliances. If you have no battery and you had about 4,000, you have about 30%, which we saw before, of self-consumption. If you put some battery in, 2.5, 5, and 7.5 kilowatts, you can double this approximately. So this is basically if you just buy one of these batteries which are here on display, or which are advertised. If you say, okay, that is a bit expensive, can I do it with my heating? Then you can see with the heating you can get actually quite a large amount of your demand covered. Obviously you have 7,100 now because you actually had to create all that additional heating also. But you can see also about 30-40% of your total demand heating and electricity you can do with your own solar. And if you now use a battery, you get some improvement, but you don't get as much. It's obviously because the battery is now doing the buffering for you. The storage, the thermal is already doing the buffering. And so the electrical battery doesn't get you as much anymore. But this is basically numbers. It's too quick to look at it now, but you can basically now check how much, if I have a certain house, can I actually get from my own system coverage. Now, sorry. Another problem. We have seen now approximate figures of 30% of self-consumptions which you can have just for your appliances. But now, there's some people that use a lot of electricity during lunch hour, and some people work all day, they just come home in the evening. Obviously, that has an influence. So the question is, how big is that influence? Because before we did just a simple case. If you really want to know it for your household, you probably have to measure it beforehand. But just to give you an idea of the spread of results that you get, that's the following graph. Here you can have two extremes. The one where you have already a high consumption when the sun shines, which I call the self-consumption high case, and the low case where you are in the evening. Obviously, the batteries will work better here in the low case because you have a lot to gain. And now you have these low case is the solid lines and the high case is the dotted lines. And you can see here the blue ones are for a small PV system, the red ones for the medium-sized, and the other one for the small, the green one for the large PV system. And what you can see on the bottom is how big your battery is. Without battery, you get about these 30%, but you can see there's already some spread, depending on PV size, some 30% of your own consumption again. And here you can see how much gain you get if you get a battery. So you can decide, is it worth it for me to get a larger battery? And you can see that if you take a big PV system, even large batteries give you a gain. It still gives you a gain. Whereas if you have a small PV system, batteries doesn't get you much because you use everything yourself already without the battery. So this gives you a little bit of a tool to check how big does your battery have to be and how big can it be with your PV size. But the rule of thumb is take a bigger PV system and your battery pays off better. If you look at it and check why, because if you have a big PV system, even in spring, on autumn, the batteries get full. If you do have a small PV system and you don't have much sun, you don't get the battery cycled, and therefore you don't get any use out of it. So it makes sense. But here you got the numbers. Now the question is, can you do something for the grid in addition? And yes, you can. If you actually charge the batteries at the earliest opportunity, what's shown here is in red for a day, just the PV injection, and in the brown curve, you basically get here in the morning the battery is being charged, and if at 12 o'clock you have the most PV, the battery is actually full. So what will happen is that the grid gets the full load. And what we're here showing is if you just delay the charging and you just tell it to sort of linearly increase the maximum allowed charge in the system, then you can sort of cut this down to some extent. It's just a very simple mechanism. And this is basically, if you look at it year, and this is trying to show you how it works in over the year. It says here from January to December, and from midnight over lunch hours to midnight again. Obviously, in summer, during lunch hours, you have the largest peaks. Now, question is, can I cut it? And yes, if you do this delayed charging that I showed to you, you get already quite a lot lower. Yeah, so you can be very grid-friendly by just a very simple mechanism. And if you now add the fact that you have maybe a heat pump, and that your hot water for showers can be also being created during lunch hours, then you can get rid of this in total, basically. And this is only a very modest cutting. So this is basically saying, okay, I maybe have 5 kilowatt peak on my roof, and I'm just basically saying I'm not putting more than 55% or 2.8 kilowatts into the grid. So basically, I can almost cut it to half, and I can basically cut all the peaks away. So I'm very grid-friendly. Now, with a smart algorithm, you can get even further. And so at the end, what we can also do and simulate, if people are interested, we can basically just put a smart energy system in, which then observes what PV production has been in the past days, which observes what your household was using, and then it controls the charging and the battery and the heat pump operation and the your pumps in the house to heat the house. And it does that smart based on a forecasting mechanism. And with this mechanism, you can even take those limits of grid loading further. So in summary, we actually do have said that for a single house with, when you do nothing, you basically get about 30% of what's on the roof created, which is being used here on its own without batteries. Now, if you use heat pumps, you can get these 30 to 40 upgraded if you use some thermal storage. And if you have a new house that you build and you decide on your energy system and your heating system, it's always a good idea to actually use heat pump. And you see this in Germany in the new buildings quite often. There's a lot of heat pumps being out in the house. And that's correct to do it this way, because really our energy system will be in future driven by electricity. If you want to get rid of coal, our sources are wind and sun, and basically the spine of our energy system will be electricity. So it's good if you now if you try to base all your energy needs on electricity. And then here, if you want to increase that, a battery, of course, helps. It can increase it to by another 10 to 30%. And what I have shown that the grid load can also be reduced if you use some smart algorithms. And since I have a bit of time left, I was rushing through it too much. Sorry. I might just take you through this last one, and you might be interested in a little bit about the amortization. Does it really pay to have a battery? And therefore, I can show you this one quickly as well. This is basically drawing here on the bottom your PV production. And this is basically what in Germany we get 14 cents, 15 cents, maybe now it's even going down to 14 or 13 and a half. This is basically what we get paid if you feed this PV into the grid. So basically that yearly production and what I'm getting per kilowatt hours, if you sum that up, this area gives you basically what you earn if you put it all into the net. And with this one, you actually have to pay your PV system. If you know that you have 30% self-consumption, and you now have an electricity price of 25 cents, and in 20 years maybe 45 cents, then this area is also what gains you, what gives you payback for your PV system. And only the increase here in self-consumption, which you get with the battery, is the one that pays for the battery. So only this one pays really for the battery. So if you really add this up for 20 years, and you take the curves that I've shown you before to see the dependency of increased value, increased self-consumption of batteries, then you get to these curves, and they basically tell you for the different profiles that I've shown you before, unfortunately this is German, that you can pay about 600 euros per kilowatt hour for the battery to make it worthwhile for you. Unfortunately, batteries nowadays are about 2 to 3 times more expensive, so it's very hard to prove a battery system in currently, a PV battery system. So it needs a little bit of personal motivation to say, okay, I want to be CO2 friendly to have a battery nowadays. You can look at it another way. You can say, well, let's look at the value of my PV system in total. And what we did here is we took the net present value of a PV system with different size of PV, with different size of battery, and you can see that the highest value of a PV system at the current feed-in rates is still if you have a large PV system and no battery. So currently, the battery has a bit of a problem. But so large PV systems are okay, no battery. But if you look at how costs develop, what happens is within the next years is PV payments in Germany are being reduced strongly. You have to rely on self-consumption, otherwise you don't pay off your PV system. So what happens is people start to build actually smaller PV systems which just match your consumption. Unfortunately, roof area is being lost. But what happens is that the batteries try to help prove in the PV systems, because now you need them because your self-consumption is the one that pays for you. So really you go through a transition now, and if you take this further, what will happen is that then you get the best deal in future if you have a battery and a large PV system, because now your system costs go down, you don't get any feed-in anymore, but electricity prices go up, and what will happen is in future that large PV systems are good again, and you need a medium-sized battery to make the best profit out of it. So we're going, unfortunately, through a very rough transition now with our feed-in rates being cut out so quickly. We go from the transition of where PV only is the best through where it becomes very difficult to where you need the battery to make it work. All right. Sorry. Then I would be at the end of my talk.
So, thank you very much, Dr. Binder. This is your applause for this informative and interesting presentation. Are here right now any question from you, from the audience? Just raise your hand and I will come to you with the microphone. Sona, yeah. Would you be so kind to introduce yourself?
Yes, I am Fernando Figueroa. I'm in the Netherlands, and well, I'm interested. How do you perceive the price evolution of batteries? Well, they are not a very widespread technology so far, so there's a potential for the price to reduce. But do you think that they will achieve this price reduction necessary to make them economically feasible, or do they need a certain help to help them grow or be cost effective?
Can you put the presentation up one more time and I can show the assumed prices? I actually think that the battery prices will come down because we are seeing the first systems now. And it's very hard for many companies that thought that was a business and that went into it to now come up with volumes to make the prices go down. I'll just show you quickly what my assumptions was. What I'm seeing from the car industry, they are already now dealing with prices below 500 euros per kilowatt hours. Sorry. here you can see what we assumed for the batteries, cost of the batteries. We said that in 2016 that they are below the 500, and then we're saying they're going in 220 down to 230 for the lithium batteries. Yeah. So, and now if you talk to car people, they're saying they get them offered for below 500. But unfortunately, of course, there is some interest from battery manufacturers to get into contact with this new development. Like they are really seeing electromobility as a big thing to make money in future. And so from their side, they actually make a commitment. And so the batteries don't have that price yet, but these companies think they can make that price. And so car companies get that price today in 2 years, basically. And if you look at that price, then I think it's right. It can work. But it's a chicken and egg problem. Like if we don't deploy these systems, if there's not the first movers, then we will have a problem. Then it can die as well. Yeah. So.
Okay. Thank you, Mr. Binder. We have time for a short question. Would you be so kind to introduce yourself?
Sebastian Werk, TU Berlin. I have just a question, how sure you are that the electricity prices will really rise? I mean, we have nowadays the lowest electricity prices on the stock market, and at least the politicians said that via the EEG the prices shall not extend more than 2 more cents. So where shall those 45 cents come from, which are more or less a crucial factor for your calculations?
Yeah, you're right. That's, of course, looking in the stars, because you know already that I would have to correct that one, because now we have to put EEG-Umlage in there. Like I'm not getting all that gain. If I use my own electricity, it's actually penalized. So there is some dependency. I think I have the number in my head that for every cent difference or less difference, the battery has to be 20 euros per kilowatt hours cheaper to make it the same business case. So you can calculate the dependency. It's not that it throws it totally out of the window, but obviously if you have 5 cent penalty, if it's not 45 cent, it's 5 cent, it's 40 cent. It's maybe not over the whole 20 years, but if for 20 years you have 1 cent different, it's about 20 euros per kilowatt hours. You can basically calculate the sensitivity, and then it's up to you what you look into the glass bowl is. Yeah, right.
Thank you. And I have to interrupt you because it's the end of the time now from your presentation. So if you have any question in your mind, please don't hesitate to come to the booth here at the group exhibit, Hydrogen Fuel Cells and Batteries. It's booth number D50. It's in this direction, and I think Dr. Binder and all of his colleagues will welcome you there and discuss any problem or question with you. Thank you for your attention.
Yeah, thanks.
And we will continue our program after a short break with a presentation from Clear Edge Power. Thank you.